Continuing trigonometric substitution, if you're looking at this part in the integral, a squared plus x squared, then you're going to consider this substitution. What does it do? That change that square root to non-square root, except there's absolute value usually. But other than that, I can get rid of absolute value. Square root. So that's why we're doing this. But let's think about sketch a situation like this on this side here. Square root of 2 plus 3x squared. What would you do? Let's be a little bit flexible in here. Square root of 2, right? We're going to take care of that square root of 2, but the tangent. But what are you going to do about that 3? How are you going to take care of that 3? You want to get rid of the 3 too, right? If you just put it in there, I will get 2 plus 6 tangent squared t. Is that right? So that's under square root. It's not perfect secant squared, right? Because of the 3 factors in there. Don't you think? So how can I take care of that 3? By further doing something to that. Divided by root 3? Will that do? If you put that thing in there, then the main idea is this one. This is what you want, 3, x squared, such that this all work out as 2 plus 2. I don't know. It's not necessarily better. So let me just erase that. If you choose that one, then you have 3 and then 3. And if you square that, you have 2 times the tangent squared t divided by 3. So you can see 2 is a common factor and pulled out. So it's a 2 times now 1 plus tangent squared t, right? 2 has square root, but that's not function part. It's a constant multiple. So for integral, it's not a problem at all. You see that? So if there's something in front of x, this is something you can do. Tweak it a little bit more so that you pull out nice 2 times the secant squared t. Does that make sense? Any question about this one? So all the other thing, if they have 2 minus 3x squared, and you probably know how to tweak this one. If I have 5 minus 2x squared in there, it's in the opposite way, then you can throw it a little bit. Your goal is that make it into perfect square, except the constant part. Does that make sense? Yeah. All right, that's the trigonometric substitution. And what was the test problem? Was that this one, sine t? Right? Okay. So here is such a problem again. We have this integral. I don't know what the integral of this one is, but if I substitute with ht, there's a theorem, right? You can just integrate this t function, and that's what the theorem is about. So what is this ht supposed to be here? 3 tangent t, and then it's going to completely switch to what kind of trigonometric integral that we've been practicing in 7.3. This is 7.4. All right? So that's what we've been doing. How about this one? Practice one more time. Square root of 2, not sine, secant t. That's right. So this is a summary. I'm emphasizing it is not some procedure I ask you to do and you repeat it. You have to recognize that these two things are actually equal to each other. If you integrate that only in your mind, because you know antiderivative exists. How do you know antiderivative exists? Even if you can't compute it. Theorem of integrability or something, right? Yeah. The antiderivative exists. But on the right-hand side is not integrate and substitute. Just integrate this one, and that is supposed to be the same answer. Okay? So I'm writing here like this. Capital F, antiderivative, only existence we know. But if you substitute back in here, that becomes g of t is something that you can compute. That's why we usually do. If I can't compute this one, I can't compute this one, why would you do this? Right? Right-hand side is something you can computable, so you have something actually worked out, and this one is just a theory, f of h of t. Okay? Yes?
Would you ever have where the right-hand side wasn't computable, so you did it again?
Well, this one gets still hard, but it might take several steps to get down to that level, but usually we wouldn't go back in here. Yeah. Right, it could happen in here. Yeah, not just immediate. It's computable. It could be lengthy, but this one usually has absolutely no idea, for example, how to do this one. So that's usually how this one kick in. But the key thing is that we computed this one all in 8 in terms of t, but our original question is what is the antiderivative of this guy, right? This is our problem. And this, what we've been doing is just a part of it. Okay? So this is our original question. We don't know what that is. But if you substitute it back, it's the same as antiderivative of this t function. So what is this capital F of x? If we arrive at here, how do you go from here to there? That's what we're doing today. Does that make sense? All right, here's a general idea. It's generally easy to describe. Well, substitution is x is ht, right? That's just what happened. X equals ht. And this is what we have here. And we want to change that one f of x, right? And ht was x there. So I can just replace that ht with x because that was a substitution. Kind of makes sense. All you have to do is how can I change that gt in terms of x? So how is x and t are related through that function? How can I write the t in terms of x? Is just reversing this function, right? Reversing this action of h, which is inverse. Okay? You know inverse is not the same as reciprocal, right? Think about x equals t squared. Your answer is not t equals 1 over x squared, right? So inverse is square root, not reciprocal. So if you can inverse it, then you're going to put it in there. But all those we're saying is trigonometric substitution, right? These are all x equals sine t, x equals secant t, x equals tangent t. When you reverse it, you just simply put arctan, arcsine, secant. Probably have to go through arc cosine because that's more common thing. Anyway, when you're doing the inverse thing, you have to know what you're doing, right? Sine inverse only makes sense in a smaller range and things like that. So that's what I mean by your substitution when you do that, and you have to understand what you're doing. But in general, mechanically, it seems like easy. Just simply go and stick an h inverse there. Sine inverse, tangent inverse, done, right? But they torture you a little bit more. But let's practice this whole thing with this example. All right. So this is easy to just pretend you can integrate this one. So you substitute x equal e to the t, and how can I introduce it if I can't integrate this one? Use the substitution method to integrate there, right? Then one more thing you have to do is that how can you calculate f of x there? All right, let me show you. Why don't you write down this problem there? Integral, this is your first exercise today. Integral x plus 1 dx, bracket, x is substituted with e to the t. Now you do the same calculation you did that in the test. At the end, throw one more question. So how can I, from that result, how can I go from there to the answer of antiderivative of x plus 1? Right? Did you all write that down? Problem? Here I'm showing you the outline again, right? So you arrive at here, right? That's something you have practiced for the past test. Go from here to there. Simply just substitute t with h inverse x, right? That's all you have to do. Okay? You got that formula in t. Change that all the t in that formula with h inverse x. All right. So that's your exercise. I hope you arrive somewhere here. If you integrate in terms of t, and this is actually the first example of substitution method 2 we did on Monday. All right, so this is a new thing. We have this result. Pretend you don't know the antiderivative of x plus 1, which is called capital F. If you substitute x equals e to the t, and that's the result. And you want to pull this out, f of x, what is it, right? Because you see e to the t everywhere, this process is not really necessary, right? If that one is called x, what would that be? X squared, right? What would that be? Just x. So that's the result of whatever the complicated thing I wrote it down there. Okay? But let's just go through them mechanically, what it arrives. So this is the form. Whatever you calculate in terms of t, now you substitute back t equals h inverse of x. So what is the x and h formulation? X equals e to the t, right? So what is t? Inverse of e to the t, right? What is inverse of e to the t? ln x. So that's ln x here. So you substitute back. So it says 1/2 e to the 2 times ln x plus e to the ln x plus c. That's the answer, right? Yeah. If you do that, you can see x is only, because your x is inside log, it has to be positive. Remember, the domain of log function is positive real numbers. So this only makes sense when x is a positive. But you know that e and ln cancels, right? They're inverses to each other. So here, but because of 2, e is not immediately followed by ln. There's multiplication by 2 is there, so you have to change that to ln of x. When 2 goes inside ln, becomes the exponent. This one's simple enough. E is following immediately after ln, so they cancel, just become x plus c. This one, this expression itself, doesn't have to be positive. X is perfectly fine no matter what the number is, right? But here, only makes sense when x is positive. And this one, they cancel and becomes ln and e. They cancel, so it's x squared plus x plus c. And that's the antiderivative of this one, x plus 1, right? This is one hard way of doing that simple problem. Does that make sense? This one, x doesn't have to be positive, correct? But logically, let me explain this probably. This is the important part. To go from here to there, right? We're using this fact. This fact is only true for the input value being e to the t, correct? But what do you know about e to the t? Can that be negative? No. Can that be 0? No. Always a positive, right? So whatever you conclude from that equation to here, only true when x is positive. Because all this conclusion is based on this fact, right? Therefore, this is the only valid thing we can conclude. However, this formula makes perfect sense when x is even 0 and negative. And you go and actually differentiate this one, because it makes sense at negative too. You differentiate it, then you realize that that's x plus 1, right? Therefore, this antiderivative not only is valid for x greater than 0, at the end, you can claim that this actually works for all real numbers. Does that make sense? Always the case. But it has to be proven. So this is only up to here prove this is true only when x is greater than 0, right? What if x is less than or equal to 0? Is this still an antiderivative of that function x plus 1? Right? So here's a question for that. Is the function we found still an antiderivative of what function? X plus 1. Somewhat is a trigonometry against square root complicated. You don't see that immediately. Then you have to actually differentiate this one and show that one is x plus 1, even if x is a negative in that range, right? First of all, when x is less than or equal to 0, this makes perfect sense. There's no problem here. You actually differentiate it and show that it's x plus 1. Does everybody see why we have to do this one? You see the need in terms of logical argument part? This needs to be explained. So you actually differentiate this one. D dx then is 1/2 times 2 times x plus 1. So that's x plus 1. That still works. That is still an antiderivative. That's right. But you don't usually encounter that. Everything is tangent and sine substitution. You usually don't encounter any of this problem. Yeah. But secant substitution get weird, and you do have to take the thing at the end. All right. Yeah. So in terms of logic, make sense? This is perfect from the substitution. From here, we conclude this type of thing only valid when this substitution for x value in here. All right. Let's see what we have next. So here's some annoying part about this section. If h and q are trigonometric, at the end you will just simply stick in tangent, arctangent, and arcsine, right? And leave it like that. How convenient. But for example, like this. But they want you to simplify this one. If it is a composition of trigonometry and inverse, there is a way to simplify it, and they expect you to simplify it. All right? So that's the next thing we're going to do. So if you're looking at a cosine t and simply stick in a sine inverse, that's the shape in there. So, but if your antiderivative is having this cosine t and your substitution is a sine t, then you can rewrite it nicely. All right? So that's the next thing we're going to do. I'm showing you this one already. So let me explain this substitution. Then I can add this as an exercise. Suppose you finish. This is a situation, and here you have f of sine t, x equals a sine t, so that's a sine t equals, you have g of t. Can you imagine? You went through and you have the right hand side ready. You have all without integral at all. You compute it completely. Now next thing is that this is going to change to f of x, right? A times sine t is going to be f of x. That means x is a sine t. And how can I change the right hand side? T is going to be all substituted as x equals here, a sine t. What is t? Because of this a, you have to do one more thing in here. First, the sine t. What is sine t? X divided by a, right? What is t? Sine inverse of x divided by a. Now, wherever the t is, you're going to just stick in sine inverse x divided by a there, right? And, okay, that's my answer. Versus every time you see cosine t, you can do actually better than cosine of, now that's t. I'm just going to stick that in there and wave your hand, and that's my answer. No, you have to go down to this level. So this whole thing is a t, so it's a cosine t. So let me explain it this way. T is varying from here to there. They usually put that to take care of absolute value stuff. The sign varies from positive to negative, but on that range, cosine is always a positive. So usually we put something there. Also, we usually put this something like this so that we can consider inverse function. All right? Before you enter inverse, you have to make a function restricted and one-to-one, and this is where standard choice of one-to-one function of sine. Okay, so if here is a situation, if t is kind of angle in here, it can be that. If t is a positive, then it is really the triangle situation. Sine t is here, sine t being x divided by a from the substitution. So if you draw a triangle and positive, and there's a t radian, where would you put your x and a? A must be hypotenuse, for example, here, right? X is the opposite side of that t, so x goes there. If t is positive, these pictures make perfect sense, correct? How about down here, in terms of a and x? Square root of a squared minus x squared, right? By Pythagorean theorem. So what is cosine t? Adjacent divided by hypotenuse, correct? So that's adjacent divided by hypotenuse. If sine t is x over a, cosine t is nicely written in terms of algebraic function of x. And that's what they wanted, rather than leaving it like this. Because it can be simplified, and this is a better expression than this. So, in session 3, test 3, probably problem number 1 is going to be do this and simplify your answer. And then that means you don't leave it like this. You actually have to enter like this. Does that make sense? All right, let's do tangent t. All right, what about here? What if a t is a negative angle? Then this angle thing doesn't make sense, right? And you have to go to the circle and so on. But you can use odd and even property is the same thing as this one, the negative t. So an even in t's in between pi over 2 and negative pi over 2, what is the sign of cosine? Always a positive, right? Cosine graph looks like this, around negative pi over 2 to positive pi over 2. So they're always a positive. So you don't have to take care of the sign there. Does that make sense? So that's why I put the positive there. For all cases of t, cosine t will be always a positive. How about in this range of tangent t? Can that be positive or negative? It can be negative, right? But you see that? I didn't put negative sign in there. So if t is a positive, then here, what is the opposite? What is the adjacent? That one, right? Tangent is opposite divided by adjacent. Make perfect sense when t is positive. When t is a negative, the same magnitude has to be up negative sign in there, right? But I didn't put the negative in there because x itself here is negative. When t is a negative angle, x is a negative number. So this x takes care of the sign. You don't need to put negative there. Does that make sense? Assuming a is a positive. We usually choose positive 2 times sin. You don't usually choose negative 2 times sine t. Makes no difference. Assuming a is a positive. Does that make sense? All right. So no need to put the negative symbol in front of tangent t. All right? So I want you to do this for tangent t. X equals tangent t. For tangent t, when is this one-to-one function? You have to look at pi over 2, negative pi over 2. Especially, I didn't make this one equal to each other, pi over 2, because tangent is undefined at pi over 2. So you have to go like that. What is cotangent t? Cosine t. Can we write that in terms of algebraically in terms of x? This one algebraically in terms of x. Draw a triangle. Always put that thing t greater than 0. That picture only makes sense when t is greater than 0. And think about t less than 0, just looking at the overall sign. Do I need to put the plus minus in there to take care of the sign in there? All right? That's your exercise. I hope you got this triangle. Agree on this triangle? Tangent being x over a. X can play the opposite of this angle t. A can play the adjacent of the angle t. So a hypotenuse is square roots of a squared plus x squared. If t is a real positive angle, then cosine t is adjacent divided by hypotenuse. That's that. And sine t opposite divided by hypotenuse. When t is positive, everything here involved is positive, so it makes perfect sense. This is the version. When t is less than 0, what happened to cosine? Is that the same one or negative? No, a is fixed, a positive number. A is fixed. Then it's the same. Cosine in that range never changes, stays positive, right? So a is a positive, and the denominator is positive, so we have to keep that magnitude the same. If t is a negative angle here, what happened to sine? Becomes a negative number, right? What about this one? And here it looks like a positive, but it's not really positive, right? When t is less than 0, is this a positive number? X here itself is a negative number because t is less than 0. Tangent is negative, so x itself is negative. So you still pick up a positive sign there, right? Both cases. So if the answer is the same, why bother? Just write it down, and that's what we usually do at the end of the day. But this is the correct thinking, right? Yeah. So, alrighty, that's the answer. For both cases, doesn't matter pi over 2, negative pi over 2, negative, they're the same formula. So whenever you see in your GT here, if you see cosine t and sine t, you can just replace that with these guys. And then it looks much more familiar looking than cosine of sine inverse of something. Make sense? Yeah. Right, only with a tangent, and for this sine, we did this one. Now, what is the last one? Secant. Let's see if we can do this one as well. Secant. I want you to try that. Secant. I realize we're running out of time, so let me just do it here. T is the angle. I switch to cosine t, that's what we're more familiar with, right? So where does x go? A is adjacent, right? A goes here. X is the hypotenuse. Adjacent divided by hypotenuse. So what is this guy? X squared minus a squared, right? Square root of x squared minus a squared. Fair enough? All right. Then what? Sine t is square root of x squared minus a squared divided by x, right? All right. How about tangent t? Square root of x squared minus a squared divided by a. Is that right? But this is only valid for what kind of t? Positive t, right? Not only is it positive t, x being here secant, it goes all the way up to actually pi over 2. If x t go beyond pi over 2, as you can see, secant hits a negative number. Then x becomes negative, right? You can't put negative side in the hypotenuse. What we mean here is x being positive value of a side. So this one is actually limited to 0 to pi over 2. Okay? Sorry about the awkward direction of inequality. So this is that. But what if t is in between pi over 2 to pi, so that x, which is a times the secant t, becomes a negative number here. X is represented by a times secant t. So magnitude is the same. What about tangent t? What happened to tangent t when t is in that range? Is it positive or negative? This is like a second quadrant, right? Pi over to the pi. Tangent t, positive, negative. Negative, right? But this is always a positive. Correct? This guy is always a positive. So this is no longer a valid formula for t being here and x being negative. Therefore, we should really write tangent t being negative of x squared minus a squared a. Right? Has to be split into two different cases. And what about this guy here? Sine t in that range between pi over 2 to pi, is a sine positive or negative? Second quadrant, sine value. Positive, right? So is the square root x, this is a positive, always a positive. What about x? Negative, right? So this guy is a negative, but we want this one positive. Therefore, this is no longer correct formula either. So here is a sine t, this time is a negative, square root of x squared minus a squared divided by x. The formula is messed up like this. But how do you go from x being here and negative x there? How do you put it into one formula? X and negative x. Anybody know one symbol that take care of that? Absolute value. So x and negative x, we can take care of it. It's all about x greater than 0, less than 0. So we can simplify it into absolute value of x down there. But this one, absolutely no. You just have to know which one you're dealing with. This is the case where this one being this angle here correspond to x greater than a, and this one corresponds to x less than a. In terms of angle, that's the correspondence. So here, the answer is that you can take care of the sine t into one formula like this one, absolute value of x, but tangent t, no way. You have to put plus or minus and know when your function is completely n greater than a and you're dealing with a plus. When your x is less than negative a, you're dealing with a negative side. All right? So this is ugly case, secant t. But you will see, one more thing I'll let you go. In that example, I think here, you will see that guy, x greater than 7. So you know you're choosing positive tangent t, right? Yeah. If there's x less than 7, when you go, when you choose a tangent t, you choose a negative square root version. Yeah. So that's the. When you replace the tangent t, you have to choose negative square root version if its x is less than 7. If it is like this, x is greater than 7, you choose. You change your tangent t to positive square root version. But all the others, no need to worry about it. Just everything is just same sign in here. Same sign in here. So here and here in the GT, whenever you see those three trigonometric, you know how to change those two in terms of x. And that's what they want in terms of this simplifying it. All right? So we do the same thing and change whenever you see that. Other than that, you will just enter sine inverse. Thank you. I'll see you on Friday.